Okay, in this example, we want to write a resonance structure. So find one of your patterns. In this case, I see there's a lone pair of electrons in the allylic position to this carbon, double bond, and one atom away is the allylic position. And so for these, we can draw a resonance structure. We can take these electrons and draw an arrow from the electrons in between atoms. This carbon has a formal charge of 0, so it has a hydrogen that's not shown. We don't want to break the octet rule, so we'll move these pi electrons onto the atom, the next atom. So this is a 2-arrow process. So a double bond here now. This last carbon then becomes neutral. Double bond here. And there's a lone pair now sitting on that middle carbon. Now, I'll pause here. Can we draw another resonance structure? And the answer is yes. We see that by drawing this resonance structure, we have another allylic lone pair. So this is a new one, right, by moving those electrons over. And so we can draw another resonance structures. Arrows start on the pair of electrons. I'm going to draw them in between these two atoms. And then these pi electrons will go on that last atom. It's going to sit right on that atom. So double bond there, and now a double bond here. And these pi electrons now sit on the atom. Okay, in terms of stability, we'll call this A, B, and C. What's going to happen here, this is something that we'll learn moving forward later this semester. When you have formal charges, the more R groups you have on the carbon, the more stable it will be. So if you count here, this carbon is bonded to 2 other carbons. And then these carbons, A and C, these are terminal carbons. They're bonded to just 1 carbon. And so for stability, B would be greater than A and C. Of course, A and C are equal in stability.